Welcome back, everyone. If you're wondering what that sound in the background is, it's the furnace here in this garage. I felt like it would add that extra degree of authenticity to let you know that I really am indeed filming these in my own garage. Actually, I don't know. It's pretty warm outside and the furnace is running. I couldn't tell you why. Let's get to the point at hand. I'd like to talk to you a little bit about some of the different tools and options we have for precision measuring. So, as we go through an engine overhaul, one of the important things that we have to accomplish is make sure that everything in the engine is within tolerance or is within the appropriate measurements that will allow us to use those components, in addition to examining these components for damage and things like that. So what I want to start off showing you is a couple different pieces we have that we can use for measuring and how those work, and also show you a couple practical examples real quickly on how we can use those tools. So first of all, I want to start with the Vernier micrometer. And the reason being is this is usually one of the toughest ones for people to get a good handle on for how we use that, how we can use this tool to make measurements. So what I'm going to show you is our micrometer first. And there's a couple different pieces on here that I want to point out to you. This is a Fowler 0 to 1 inch 10 thousandths indicating micrometer. That's indicated by the fact we have 0 to 1 inch on the arm here, and then we have it showing a 1 in our 10 thousandths place in inches. So that tells us that we can measure down to 1/10,000th of an inch, which is pretty precise. Depending on what we're measuring, a lot of aircraft engines will only have you measure down to the thousandths place, which is this third decimal right here. But with a lot of automotive things, you may be measuring at 10 thousandths. What I've done over here as well is I've laid out how our measurement is going to work as we take a reading here. So we have our units in whole inches. Because this is a 0 to 1 inch micrometer, our maximum reading is going to be 1 inch. So more likely than not, this number is going to be 0. If we had a larger micrometer, like this 2 to 3 inch, then our maximum reading could be 3 inches, our minimum reading could be 2 inches even. So that means that most likely our number would be 2 before the decimal point. And then we have our places for our following decimal measurements, our tenths, hundredths, thousandths, and 10 thousandths indications. On the micrometer itself, I want to show you a couple components here. We have an indicating window here, which a lot of people like to use, but it only indicates out to our thousandths place. So we still have to know how to read this Vernier scale on the micrometer. We have our anvil right here, which is what captures what's being measured in between. We have a friction lock here, so once we take a measurement, we can twist this lock to hold the indication in place. We have a slip clutch, which is used to bring this in contact with what we're measuring without over tightening it and throwing off our measurement. And then we have our thimble on this side, which is what we move to make our adjustment. So I'm going to loosen the friction lock here real quick. There we go. And spin this out a little bit so you can see some detail. Now what you'll notice is on the barrel of our micrometer here, we have our indications in tenths, 0, 1, 2. Those are whole tenths. In between, these little hashes are thousandths in increments of 25. It's broken into 4, so we have 0, 25 thousandths, 50 thousandths, 75 thousandths, and then a whole tenth. The way that this works in tandem with our thimble is you'll notice I have indications marking 0, and as I turn it around, 5, 10, 15, 20, and back to 0. What you'll notice is right now when I have this 0 aligned with the line that our tenth scale is on, I'm perfectly aligned with that 25 thousandths hash just after the 2. If I rotate this another 25 and align it on that line, again, this has brought us in line with our 50 thousandths hash. So we've moved 25 thousandths. This is important. The last piece we have on the top of our barrel here is the 10 thousandths indication on a Vernier scale. And the way a Vernier scale works is when we find our measurement and we lock this in, we're simply going to look on the top of the barrel and see which one of these hashes is perfectly aligned with the hash that's on the thimble. that hash that's aligned is going to be our indication in 10,000ths. So let's put that on hold for a minute. I'm going to show you how we can make this measurement. And I want to show you another tool while we're in the process. Now, this is considered an outside micrometer, meaning it's going to measure from the outside of an object. But what if I want to get a measurement inside of something like a hole? Well, that's where I have a couple different gauges that can be used. I have a ball gauge, which is nice for measuring small spherical parts. All that happens is I have a twist lock on the bottom here, and as I rotate this out, you'll notice that it moves this cone up at the top, which spreads this ball in the middle. So all I would need to do is insert this in to whatever I want to measure, rotate this until it just contacts the sides. I don't want it tight so that it gets stuck in there. I just want it to just contact so I can get an accurate measurement. I would keep in that position, pull it back out, and then I'll take a measurement with my outside micrometer. So I can transfer an inside measurement to be used with an outside micrometer. Another tool I have for this purpose, which I'm going to show you here, is our T-gauge. The reason they call it a T-gauge is if I loosen the friction lock here, it looks like a little T. There's actually a spring in here that pushes these arms out and fills the space inside an area. So when I get ready to use this, I'm going to push these in like so, and then I can lock it using the friction lock on the bottom. Now I'll demonstrate with this piston pin. As I insert this in, when we choose our T-gauge, we want a T-gauge that's going to be larger than the diameter we're trying to measure so we can squeeze it in and get an accurate measurement. But once I have it inside the bore, I'm just going to loosen my friction lock there. It'll snap open. And what I like to do is just give it a little twist side to side and then give it a little rock up and down. Because this is a circle on the inside and these little arms are sprung, if I give it a little bit of a rock or a shift, it's going to naturally settle in the widest point, which is what I'm trying to measure anyway. I also want to make sure that this is going into the bore as straight as possible. If I have it turned one way or the other, it's going to throw off our measurement. So I want to make sure that this is as straight as possible. And when I'm using larger T gauges, a lot of times I'll use a speed square or a carpenter square or something like that to make sure that I'm going in straight. So I have this locked in. I'm going to twist my friction lock to hold it. And now I can pull this back out and I'm ready to take a measurement. So let me show you how this works. We'll take our micrometer. Going to loosen this so that we can get the T-gauge inside. And in this case, I just like to set this right on the bench because it's a little bit easier to work with that way. So I'm going to continue to loosen this until this can slide in. And when I tighten this back up, I want to hold my T-gauge so that it's in line as much as possible with the anvils on my micrometer. I'm going to switch to using my friction or my slip clutch here to bring it in against my measurement. So I'm going to turn it until it clicks. When it clicks, that's enough friction to make the measurement. I can now turn my friction lock and remove the item I'm measuring. So now let's break down how we read this measurement. So I have my measurement locked in from what I've transferred off the T-gauge. Now we're going to decipher what we have as a measurement here. Now, first off, this is a 0 to 1 inch micrometer, which means my first number is going to be a 0. It's not 1 inch even. I haven't gone that far in the micrometer, so my first number is going to be 0. That's my whole number. We have our decimal point now as we break this into our fractional measurements. So let's take a look at what we have here. As I look at the barrel first, we count our hashes over here for our tenths place. We'll see right here that I am just past the number 5, which tells me 5 tenths. So as I write this down, my number right here is going to be 5 tenths. Now I need to figure out what our thousandths place is. Now the easy way to think about this is a 5 tenths is going to be 50 hundredths or 500 thousandths, right? So we're going to add our thousandths onto this number. So in this case, because I'm right at this even number right here, all I need to do is see where my thousandths indication on the thimble lines up on the barrel. Now this line running right across, that is my indication. And I can see where my thousandths hashes line up on that. So I have the number 10 right here for 10 thousandths, 11, 12, 13, and I'm not quite to 14. So what I'm going to do is write 13 rather, right in here, because we're indicating 13 on our barrel. Easy enough. And then we're going to find our 10 thousandths place when we take a look at where it lines up on the Vernier scale. And I can use my window here to indicate. We can see that it just hasn't quite rolled over the number 4. We can still see the 3 right there, and we're reading 0.513 at the moment. And that is what we have listed here. The last piece is we want to find out our 10 thousandths measurement. We're going to do that by taking a look at our Vernier scale on top of the barrel. Now what I'm going to do is roll this around until I see a 10 thousandths line that lines up with one of these thousandths hashes. It'll be pretty obvious which one it is. You can see as I bring this closer, a lot of these aren't quite aligned as we look at it dead on until we get to 9 10 thousandths. That is perfectly aligned right here with that line on the thimble. So our 10 thousandths indication is going to be 9. So when I write this down, our total measurement that we have transferred from the inside of our piston pin is 0.5139 inches. Simple as that. Show you another example very, very briefly. I have the piston right here. I'm going to take an outside measurement on this piston. Now, something that's interesting to know, the diameter on this piston is indicated to be measured about 0.63 inches from the bottom of the skirt. And right here I've made, you probably can't see it real well, I've made a little Sharpie mark so I know where to align the micrometer when I take this measurement. So again, I have to use a different micrometer. This is my 2 to 3 inch micrometer, and similarly I'm going to get my measurement. Now, one of the difficulties when we take measurements on something that is round like this using a flat surface is we have to make sure that we get this right in the middle. Otherwise, we'll throw off our measurement and it'll be skewed. So I'm going to start bringing this in. On this particular micrometer, our slip clutch is actually this big black band right here, so I'm going to rotate that until it clicks. And there it goes, it clicks. I'm going to lock it, and then something I like to do when I'm measuring something like this is I'll just move it a little bit forward and back to see that I've actually caught the widest point. When we measure a circle, right, there's only going to be one portion of it that is the widest point. And if I am off, then I won't be able to move the micrometer through, but in this case, I can slide it past, which means I got an accurate measurement. So let's go through and read this again. We have no indicating window on this, so it'll be a little bit different. I'm going to write our places in again, and then we can do the math. This is a 2 to 3 inch micrometer, and we have not reached the 3 inch point yet, which means that our first number is going to be 2. Easy as that. Now we're going to take a look at the barrel. This one's going to be a little bit different. You'll see there's our 9 for the tenths indication, and then we're 2 hashes in. So we'll worry about that in just a minute. But right now we're going to focus on our tenths, which is 9. All right. So I'm going to write down 9 in our tenths place. Now let's take a look at the next piece. Our 5, you notice we have our 4 hashes in between our tenths for our thousandths indication. This is going to be 25, and then we add another 25, right? So we're actually at 50 thousandths right now. Now, or sorry, rather 50 hundredths, 50 hundredths. Now, as I take a look here, I'm going to blend this out to our thousandths measurement. We have our 0, we have our 1, and then we are just almost about perfectly aligned on that second hash right there. So I'm going to take that 2 and add it to 50. So 50 plus 2 is going to be 52. So for my hundredths and thousandths, I can write 52 right there, which gives us 52 hundredths, or in this case 952 thousandths. Anyway, now onto our last number. We're going to move to the top of the barrel to find what our vernier indication is for our 10 thousandths. Now as I roll around here, let's see. Oh boy, look at that. It is lined exactly on the 0, which tells me that my measurement here is 0 on my 10 thousandths place. We just happen to hit it on the thousandths even. So we have a total measurement of 2.9520 is our total measurement on the outside. Now, another tool that you're probably familiar with is our dial caliper. This is a pretty useful tool for making a number of measurements. However, again, the limitation on this is we are limited to an indication in thousandths, as we see on the dial right there. Another thing that happens with these is the inside jaws tend to get a little bit dirty, so it's advantageous to keep a rag around to be able to wipe these off before you take measurements. Of course, we have two sides with our dial indicator, our dial caliper. We have our outside measurement and our inside measurement, depending on what we're trying to take. The last tool I want to show you is our cylinder bore gauge, which is just a different format of a dial indicator. A dial indicators are different because rather than take a dimensional measurement, they actually measure displacement. So they tell us how much we're deviating from a given measurement one way or the other. The way this works is pretty straightforward. If I'm going to take a measurement of a cylinder bore, then I'm going to set my bore gauge for whatever measurement that's going to be. So in this case, I've already gotten the measurements for the cylinder bore on this engine block. And the way that I set this up is I set my measuring device to that bore measurement. And then I drop it right into... Sorry, I'm trying to show you on video here, and this is kind of a fiddly one because it's difficult to manage with both hands. So I'm going to slide this into my inside measurement, which is already set. I have the lock set on my dial caliper. And what I'm going to do is now adjust this front bezel so that it reads 0 at this point in time. I want this to be my neutral setting. I indicate 0 at this measurement. So whatever I measure inside the bore is going to tell me if I am underneath or over that specific measurement. In this case, I've set it to the service limit for the cylinder. And get a good look at the dial right there. You can see I have it taped with plus and minus so I can remember which side is reading which way. But that's all we're looking at. Now as I push this in, right, there we have our neutral indication. If I'm larger, then I'll indicate to the positive side. If it's more narrow, then I'll indicate to the negative side, and that can tell me where I stand. So the way this works, when we take measurements on a cylinder bore, depending on what we're working with, a lot of times they'll indicate that we have to take measurements at multiple areas. You'll get, at the bare minimum, 90-degree measurements. So in order to accurately measure, we need to take a measurement this way, and we need to take a measurement this way. In addition, you may get different depths inside the cylinder that you're supposed to take measurements at. For instance, if I wanted to measure the overall taper of a cylinder, I would need to take a measurement up at the top and then another measurement out at the bottom and compare those two readings. So just for the sake of example, I'm going to show you how this works and try to get some close-ups if I possibly can. We'll see how this works, trying to do it with just the two hands. At any rate, in order to get this set up, I'm going to slide the sprung prong sides of the bore gauge inside. I'm going to push up, and then I'm going to rock it in just like so. Now what I'm looking at on the inside is where the top line for the piston ring travel is, because it doesn't do me a whole lot of good to measure where the piston rings are not going to travel. So as I zoom in here a little bit, if I can zoom in here a little bit, I'm going to just gently rock this back and forth a little bit until I get my maximum reading. So just back and forth a little bit until the needle doesn't want to move as much. There's kind of my neutral spot. Again, inside this circle, if I find that one measurement where it evens out, that's going to tell me where I'm at. So right now I'm indicating about 2/1000ths, right? I can count maybe almost 3/1000ths that I am underneath my service limit, which is a good thing. I want to be underneath my service limit. Now what I'm going to do is I'm going to push this in down to the bottom of piston travel. And again, I'm going to rock back and forth until I get the needle to find its dead spot, which is right about there. Just like so. And I'm indicating about 2/1000ths right there. So I was almost 3/1000ths up at the top. Now I'm just about 2/1000ths underneath. Let's take a look at the math side of this. So my first measurement, when we indicate something off of a dial indicator, it's going to be based on what our deviation is from that measurement. So in this case, up at the top of the cylinder, I measured, we'll call it 3/1000ths under. So we would indicate that as minus 0.003. At the bottom, we measured minus 0.002, or 2/1000ths. So these two measurements, the difference between them is going to be our taper measurement. So the difference between -2 and -3 is going to be minus 0.001. So we have 1/1000th of difference between those two measurements, which is the taper for the cylinder. Now, on the other hand, if I was taking another measurement and I went to the positive side of the scale, the math would be the same. If I had, let me flip this page over. If I had a measurement of, let's say, -3/1000ths, and I went on the positive side of the scale, so larger than that limit I set, I would indicate that as positive, let's say 2/1000ths, right? And because we're dealing with negative and positive, when we look at the difference between these two, it's actually a difference of 5/1000ths of an inch. That would be the difference between the two. So if we're making out of round measurements, if we're making cylinder bore measurements, things like that, that's how we can do the math on that and figure that out. Thanks for watching. Hopefully you understand a few of these tools a little bit better and how we can use them. We'll catch up on more of this a little bit later.